You might have seen visualizations like this that are used to demonstrate why the derivative of x squared is 2x. A similar picture, but in 3 dimensions, can be used to demonstrate why the derivative of x cubed is 3x squared. In theory, this continues to higher dimensions, but the thing is, we can't visualize them. What if I tell you that there is a way to visualize the power rule for any n, even non-integer or negative n, just that we need to use complex numbers? I know it's a bit weird to involve complex numbers, but I promise it's worth it because the derivative of logarithm and exponentials fall out very easily that way. Here's everything you need about complex numbers for this video. Every complex number a plus bi corresponds to a point AB on the plane. You can also use polar coordinates to describe this point. With coordinates r theta, the complex number can be written as r e to the I theta. If you're wondering why the exponential comes up, there are a couple of videos on my main channel about this. The upshot is that using this polar form of complex numbers, taking a complex number to an nth power becomes much easier. R e to the I theta becomes r to the n e to the I n theta. So it should correspond to a point with polar coordinates r to the n theta. That's what the power function does to a complex number, and let's put this aside for a moment. What about applying logarithm to a complex number? Well, it becomes the real logarithm of r plus I theta. The polar form doesn't give us anything useful, so let's leave it like that. So the log of the polar coordinates r theta gives ln of r plus I theta. Again, we put this aside for later. The final function we need is the exponential itself. However, starting from the polar form isn't too convenient, so we start from the plain old a plus bi. The exponential function gives e to the a times e to the ib. The output is already in polar form, and the polar coordinates are e to the a, b. Again, we push this aside for a bit. The next step is to look at their derivatives through the lens of complex numbers. Let's start with the power function, raising a number to the power n. So a number r on the real axis is transformed to r to the n, and a nearby point, r plus h, is transformed to r plus h to the n. Now, by definition, the derivative of this function at r is the limit of the ratio between r plus h to the n minus r to the n, the difference between the 2 points after you apply the power function, to h, the difference between the 2 points before you apply the power function. In other words, how this difference scales by raising to the power n. So the derivative is the scale factor of this difference, and we are about to harness the full power of complex numbers. The idea is to make this new point have polar coordinates r theta for some very small theta, which means this new point lies somewhere on the big circle of radius r. This means two things. First, this is a circular arc with radius r and subtends an angle of theta, so the length of the arc is r theta. Second, since we are only taking a small angle theta, the displacement from r is pointing almost vertically up. We cleverly chose the displacement to be vertically up with a length of r theta away from the real axis. What does it look like after raising everything to the power n? From the result we had earlier, we know that the new point must have polar coordinates r to the n theta. In the picture after the transformation, We can reuse the argument a minute ago. The new point lies on a circle with displacement r to the n times n theta away from the real axis, because this circular arc has radius r to the n and subtends an angle of n theta. Again, for a small enough theta, the displacement from r to the n is almost vertically up. Therefore, after raising to the power n, the displacement has length r to the n times n theta. From the original vertical displacement of r theta to now being r to the n times n theta, the derivative of the power function, the scale factor of this displacement, is equal to the ratio r to the n times n theta to r theta, which is n times r to the n minus 1, exactly the power rule. What I like about this is that each part of the expression has a meaning. The factor n comes from scaling the polar angle, and the factor r to the n minus 1 comes from scaling the radius from r to the n. It is also not restricted by dimensions, because the mapping between the polar coordinates works for arbitrary n, even for non-integer or negative n. Of course, since this argument uses complex numbers, it's a little bit more involved than the square or the cube. But I would argue that using complex numbers is a lot more elegant and general, and is applicable to other functions too, like the logarithm. The logarithm sends a point with polar coordinates r theta to ln of r plus I theta. A point r on the real axis is mapped to ln of r, and the logarithm sends the nearby point with polar coordinates r theta to somewhere vertically above ln of r. In fact, exactly a distance of theta away, because that's the imaginary part of log. Again, the derivative is asking for the scale factor of the displacement after applying log, and in this case, it is the ratio of theta to r theta, since we went from the original displacement of r theta to theta after applying the logarithm. This ratio turns out to be 1 over r, which is exactly the derivative of log that we expect. Just for good measure, let's consider the exponential function as well. However, unlike the previous cases, we don't displace the point along a circular arc. Instead, from a particular point A on the real axis, we displace vertically upwards with a small distance b away. Then, we can use this formula to see where this point goes under exponentiation. It should go to a point of distance e to the a away from the origin with polar angle b. By this point, you probably know the drill. Since the point after transformation lies on the big circular arc with radius e to the a and subtends an angle of b, the new displacement is e to the a times b. Again, since we started with a small b, the displacement here is almost vertically up. So, from the original vertical displacement of b, it becomes a displacement of e to the a times b. The derivative, which is the scale factor of the displacement, can then be computed as e to the a itself, exactly what we expected for the derivative of exponentials. So far, what we did is actually building the intuition of taking derivatives of complex functions. For complex functions that map a complex number to another complex number, generically, the displacement isn't just scaled in length, it can also change directions. In those cases, we say the scale factor is complex when it also involves rotations. If you want to know more about this intuition, go read Visual Complex Analysis by Tristan Needham, where this video is based on, and if you want to watch videos instead, there is already a video by VCubings that talks about it. Links in the description. Thanks for the patrons, don't forget to like, subscribe, and comment. See you next time.